everyone. My name is Marius. I'm an engineer at Arcium. Today I'm with my colleague Nick, who is a senior cryptography engineer at Arcium, and we are going to talk about Cerburus, which is our more security-focused backend. So yeah, please Nick, what is Cerberus?
Yeah, so thank you for the introduction, Marius. So I'll go through this very quickly, and we'll get into it later. So Cerberus is additively secret shared. MPC protocol, multi-party computation protocol, which is secure with a board for a dishonest majority. And it supports scalars, finite field elements, booleans, and elliptic curve points.
Okay, thank you, Nick. So this is quite a lot to digest. Could you please explain to our audience, point after point, what you exactly mean by these terms?
Yeah, absolutely. So we'll start by the simpler of them, which is secret sharing. So the idea of secret sharing is very simple. Say you have a value x that you want to distribute among different players. So we'll call them P1 up to Pn. You want to distribute it in a way that a certain subset of these peers is able to reconstruct the value if they put them together. So let's say you give xi up to xn. So that's generically secret sharing. There's a lot of ways to do this, but additive secret sharing is the simplest way. And here you have the xi's. When you sum over them, you can recover the original value. That's how you recover it. You need everyone's value to recover it.
You were saying that you need everyone's value to recover the underlying plaintext value x. So as an individual player, what can you learn about x?
Yeah, so that's the cool thing about this. If you only look at the individual shares, you don't actually learn anything about x. They look completely random to you. And it goes even further. If you sum all the xi's but just forget one, so you have n-1 peers coming together, they still can't learn anything about the underlying value itself. You really need everyone's value.
Okay, thank you very much. So that is pretty impressive. Next point is secure with a board. Could you please explain to our audience what that means actually?
Yeah, so the idea here is that we assume there's at least one honest player in this computation. If they all collude, it doesn't really work. But you have one player that you know follows the protocol correctly, and then all the other ones can do whatever they want. And the idea here is that if that player detects some kind of misbehavior, he's able to signal on the board something which he sends to everyone else in the computation saying, I'm done, I saw some tampering, I'm not continuing with this computation, and everything ends there. So yeah, that's the idea of secure with a board.
Okay, so a bit more concretely, please. How can the honest player detect that there has been misbehavior amongst at least one other player?
The idea is that when you distribute these xi's, you don't just give the xi to the player, you also give something called a MAC. And MAC stands for message authentication code. So you also get not just xi, but the MAC associated to xi. And how the MAC is calculated is with this very simple formula. You have alpha, which is a constant, xi times xi plus beta, which is also a constant. And so the strength in this formula is that these variables are known to different peers, right? So let's say you have the receiving peer in red, which knows alpha and beta, and the sending peer, which knows the MAC and xi. And so when the sending peer wants to send a value to the receiving peer, he sends the share, obviously, but also the authentication of the share. And when the receiver gets that, he knows alpha and beta. He will check that this MAC that was given to him is equal to alpha times xi plus beta. And so if it's not the case, you see that there is tampering because the sender does not know alpha and beta, so he's not able to construct this MAC for an unknown value xi.
Okay, thank you. So as a sender, I know xi. I do not know alpha and beta. How is it possible for me to correctly compute the MAC of xi?
Yeah, so we won't go too much into this video, but assume you have this black box functionality, which we call fauth for authentication. And on the one side, it will take different things and output something else. So I'll use different colors to represent what each party knows. So the sender knows xi, right? And the receiver knows alpha and inputs it. And the functionality then outputs beta on the other side and gives the MAC, the corresponding MAC to xi, to the sender. And so in the end, you recover the ownership that we see in this formula. So it's a bit of a black box, but we assume it's there and it works.
Okay, thank you. However, I assume that this black box functionality, you call it only for input data. It's kind of a pre-processing step. How do you propagate properly the MACs for intermediate values? Could you please provide us the example where you add two secret shared values with their respective MACs?
Yeah, exactly. So as you said, this is something that you do beforehand. It's quite a heavy step, so you don't want to have to do it during the actual computation. So the way that, let's say you have two secret shares, which we represent with these two brackets. You have x and y, and you want to add them together. You want not just to add the shares themselves, but you want to keep the MACs consistent. And in this case, and you can check it yourself, the way that you add them together is that you get xi plus yi for the shares. And then for the MACs, it's also an additive relationship. So the MACs are homomorphic. And so you get the addition of both MACs. And the way that you adjust the key, the alpha and beta, so that this works, is that the new key is equal to alpha, which doesn't change, and beta x plus beta y. And you can check for yourself that this relationship is consistent.
Okay, thank you very much. So that means for every variable of your protocol, of your circuit, you can basically propagate the correct MACs.
Yeah, exactly.
You were saying that the authentication takes place whenever a value is opened. Mm-hmm. When is the earliest moment you can detect misbehavior in your protocol?
The earliest you can detect is when you communicate with other peers, because that's when the MAC check-in happens. And during the protocol, that happens during what we call openings. So openings, as the name might suggest, you have everyone put their shares together and then reconstruct the underlying value x. And yeah, so everyone sends each other their share and the MAC associated, and that's where the checking happens. So the idea is that because even if this is a local operation, right, you add two shares that only you know, if you have tampered with any of these MACs that come into this, the MAC of the resulting share will also be wrong. So you can tamper with a value at any time during the protocol, even with local operations, but at any point where you open that and the MAC gets checked, you will automatically trigger an abort.
Okay, thank you very much for these explanations. There is one last point here on the whiteboard, namely the support of different backends. Could you please expand a little bit?
Yeah, sure. So the idea is that we support scalar fields. So this is scalar fields, booleans, and elliptic curve points. So booleans, I think everyone familiar with programming knows what those are. Then scalars, they act very much like integers that you might know, but they overflow naturally, and they go up to some constant p, which is a prime in this case, and then overflow back to 0 as soon as they go p plus 1.
Okay, thank you. And there is one last point here, the elliptic curve points. So I'm very curious to learn in what situations you would use this backend.
So the idea here is that imagine you have some kind of cryptographic protocol that uses elliptic curve points. So for example, a ZK proof. If your MPC protocol didn't support elliptic curves natively, and you wanted to do the ZK proof within an MPC protocol, you would need to emulate these elliptic curve points and emulate them using booleans and scalars, which turns out to be a lot more expensive than just using EC points locally, because you would need additions, of course, but also multiplications. And multiplications within our protocol, multiplications of scalars, are relatively expensive because they're interactive. You need to send information to other peers, so there's some communication overhead associated to that. And so if you're just able to do things fully locally, that's a huge boost in performance. So that's why we integrated this also into our backend.
Okay, thank you very much, Nick, for explaining Cerberus. The next question is, what kind of applications did you have in mind when you decided to implement a backend with the highest standards of security?
Something that needs security, for example, smart contract applications, anything that manages money, that relies on the output of a computation being correct. And in this case, as long as you assume at least one player is honest, you are able to trust fully the output of the computation. So this is quite a strong requirement. In our case, because we support scalars, booleans, and elliptic curve points, you're actually able to turn any piece of code, even high-level code such as Rust, into a Cerberus circuit. That being said, some examples of applications that take particularly good advantage of the security would be, for example, smart contract applications. As I said, anything that needs a high level of security, that manages money, or cryptographic applications. Which take advantage of the backend directly. Maybe they act on scalars and elliptic curves directly. They will take fully advantage of the backend, so obviously these are particularly appropriate, but you can code anything in using these circuits. So yeah, we can't wait to see what you actually come up with.
Awesome, thank you very much, Nick. So today we have learned about the type of secret sharing, we have learned about the security model of Cerberus, and we also have learned about the different backends that you support. Where could our audience have more information about what Arcium does?
Yeah, so obviously we'll leave some literature in the comments for people that are interested in the actual protocols themselves. And for more general information into Arcium, the infrastructure, and people can also refer to the Arcium docs for a more comprehensive overview of everything that Arcium does and the infrastructure.
Thank you very much.
Thank you.